Let me introduce Professor Anders Madsen to you. Anders is very well known in our community. He's associate professor at the Department of Pharmacy at the University of Copenhagen, Denmark. Got PhD in chemistry from the University of Copenhagen and European Synchrotron Radiation Facility, being for a long time in the group of Professor Signe Larsen, whom I hope is also taking part in this lecture. Welcome, Signe. Anders' research interests are focused on structure property relationships in solid-state molecular crystals, dynamics of crystals, computer modeling, crystallographic method development, machine learning in crystallography. As a PI, Anders has been very successful in getting different grants, plenty of Danish grants from Danish Research Council, Carlsberg Foundation, Willum Foundation, and Lundbeck Foundation. Anders published so far 56 peer-reviewed publications, which have earned almost 7,000 citations, presented 22 invited oral presentations and several popular lectures. Also, he's been awarded several awards, such as Young Elite Researchers Award of the Danish Council for Independent Research, Steen and Ingrid Arlands Award of the Royal Physiographical Society, Lund, Sweden, Young Scientist Award of the International Union of Crystallography. He referees for plenty of different journals, including such prestigious ones as Nature, Nature Chemistry, different ACTAs, IUCRJ, and many, many others. Also, Anders' review for the Swiss and Polish National Science Foundations, and is editing associate editor of IUCR newsletter. Anders is also on quite a few different important boards, such as the Executive Committee of the Danish Chemical Society, chair of the Danish National Committee for Crystallography, member of DANSCAT board, which is very important in Scandinavian countries because this board is giving money for different large-scale facility experiments. Anders is Danish delegate at the European Crystallographic Association General Assembly through many, many years. And also he was delegate at the International Union of Crystallography General Assembly. He's publicly very active, presenting plenty of different lectures on different aspects of crystallography and drugs for high school students and high school teachers. And also Anders teaches a lot, plenty of materials chemistry, mathematics, crystallography, advanced crystallography, pharmaceutical modeling, different master courses. So Anders, the floor is yours.
Thank you very much, Christoph. I have never been introduced in such a thorough and kind way, so thank you very much. Yes, so let's jump into it. Today we are going to talk a bit about something that I have coined dynamic quantum crystallography, and the very fancy title here, thermal motion in crystallography seen through a quantum mechanical looking glass. I was thinking that I needed a fancy title because I think this is a little different from what you have seen in other quantum crystallography sessions. So let's see if I can get you hooked onto what I'm gonna tell you about. So here's a bit of an outline of what I would like to tell you. So first of all, I'll give you a short overview of what we do. What is the pharmaceutical materials research that we do in my group, and in particular, in order to introduce the sort of topics that we are gonna, or the crystal systems that we are gonna look at today, it's important to know something about drug stability and polymorphism. It's also something of an importance to know about lattice dynamics. I'm looking very much forward to the next talk because I hope that I'll learn even more about lattice dynamics there. And what is actually the relationship between lattice dynamics and diffraction measurements, single crystal diffraction measurements, elastic diffraction measurements, as we normally do in crystallography. And then when that has been sort of sorted out, I'll talk about dynamic quantum crystallography, in particular what we have coined normal mode refinement. And then I will give a few examples, an application to a drug called pyrocinamide. And after that, as a bit of a surprise, I'll jump into something else, which I won't tell you what is yet. Then I'll talk a little about the latest developments we have in this line of research here, and an advertisement about a server where you can actually try out some of these ideas that we have about refinement using lattice dynamics. This is where I'm situated. For a long time, I was in Signe Larsen's group, which is like 200 meters from these two buildings here. But that was at the chemistry department. Now I'm at the pharmaceutical department. We educate about 200 pharmacists each year. Many of them go into the drug industry, the rather large Danish drug industry. Here's the group, a slightly old picture, unfortunately, but the best one I had of our group called Materials and Manufacturing Group. We are particularly interested in solid state materials. How do we actually, or I am, how do we ensure that we have a crystalline or amorphous product that we can actually use in manufacture some nice tablets, for example. 80% of all drugs are distributed as tablets, so basically they are crystalline. Yeah, it has been like that for a long time. If you look at your phone, perhaps you can see that it has changed a bit since 1850. Now you have a fancy smartphone, but actually pharmaceutical products in terms of tablets haven't developed very much. They look more or less the same for the last 100 years. So that even more important is then to know what is a tablet, what does it consist of, what is the crystalline state inside. Why is that important? Well, let's take a look at this scheme here. We can, of course, we would like to make some tablets that are, if we go a bit backwards according to these arrows here, we can start with the human body up here. We need some drugs that can actually be taken in by the body, that can be absorbed, where there's a certain bioavailability of the drug. And since it's the drug is often a tablet, it's the crystalline phase that needs to be bioavailable. That means that it has to have a certain solubility, for example, in order to be, and dissolution rate in order to be processed and taken up by the body. But if we want to make some tablets, we also need to have some powders, some crystalline powders, and they have to be manufacturable. So they have to be able to be processed. The mechanical properties and the surface properties of these crystals have to be considered in the manufacturing process. And that goes all the way down to the individual particles, what are their size and shape and so on, which again is dependent on, of course, the crystal structure. What polymorphic form do we have? Is it a solvate or not a solvent? Is it a hydrate? What are the different stabilities of the different crystalline forms? So that's really the heart of this drug design or drug dosage form design and the materials chemistry that is embedded in that process. Here's a particularly nasty example of a drug where the materials chemistry wasn't really well understood before it was marketed, perhaps you already know this, ritonavir disaster. So if we go back into the summer of 1988, Novia had these semi-solid capsules of this HIV or AIDS drug. It was important for all HIV patients, and they had marketed this, and it had been working for a while, perhaps a year or two, and then suddenly what they found in the production and also in the final capsules of this semi-solid form was that something had went wrong. The solubility suddenly changed dramatically so that they couldn't produce the solid forms anymore. And what had happened, they found out after using many millions of good dollars, is that a new polymorphic form had appeared, and that of course meant that they had to reformulate the drug, and it made quite a substantial impact, not only on of course the company and their earnings, but also on the patient side. Now, ritonavir is a fairly complicated system, as you can see out here. As a sort of a model system, it perhaps not really ideal to look at polymorphism. So let's take a look at something a little more simple. We're going to look at this drug here, pyrazinamide. Pyrazinamide is an anti-tuberculosis drug, and it's a small and rigid drug molecule, so it's more easy to kind of comprehend and understand what is going on. It's easier to model, for example, with ab initio methods, as we will do or show how it's done in a moment. But if we look at the sort of the terminal events that happens when we put pyrazinamides, the different forms, there are 4 different known polymorphic forms. If we put them into differential scanning calorimetry equipment, what we observe is a number of phase transitions, and we observe that all the polymorphic forms actually transform or melt at exactly the same temperature. And that's because they all transform to the same form during the heating process. So if we take note of these different solid state transformations that we can observe in the DSC here, then we can construct a temperature energy diagram. So on the axis here we have the free energy, and on the horizontal axis we have the temperature, and we can sort of construct a tentative diagram of how these different forms must converge. So we know certain things. We know that at a certain temperature of 25 degrees Celsius, the delta form becomes less stable, for example, than the alpha form. And we know that the alpha form is transforming into the gamma phase at 155 degrees Celsius, and so on. So we can sort of build up this piece of puzzle here, and we can learn how the different forms are related in stability. Of course, we don't know the exact thermodynamic transition points. These may be kinetically hindered, these different phase transitions, and so there's still something that isn't known, but at least there's something that points to that the alpha form and the gamma form are the most stable forms at higher temperatures. We can see that the curves here, the free energy curves, are a bit steeper than the curves of the beta and the alpha form, beta and delta forms. And that's all related to what we call polymorph stability, and we can draw these enantiotropic and monotropic diagrams of the free energy as a function of temperature. So if we have two polymorphs that where the free energy curves crosses, we have a change in the thermodynamic stabilities, and we see here in this diagram, for example, that the A form here is more stable than the B form at low temperature. And at higher temperatures, after this phase transition point here, we have B as the most stable form. Whereas in other cases, we will have a monotropic relationship between the polymorphs, and for example here we have B as the most stable form at all temperatures. This all relates, of course, to the free energy. So it all relates to Gibbs free energy, so which is, of course, as you know, a function both of the enthalpy of the system and of the temperature and the entropy of the system. So the entropy is really a determinant here, because of course that is multiplied by the temperature here, and that will change significantly as we heat the system. So if we have a polymorph with a very high entropy, it's going to have a fairly steep curve here, and it will sort of overtake the other forms as we heat them. It will become the most stable form at higher temperatures if it has got a larger entropy. And that entropy can be both, that can originate both from having disorder in the crystal form, or it could also be due to higher thermal vibrations, giving rise to vibrational entropy in the solid state. So let's take a look at these different forms of pyrocinamide. Here we have some energy diagrams showing that they are quite different. There are some similarities though. So the alpha and the beta and the delta form, they all form these dimers of pyrocinamide molecules that are then packed in different ways. So we have these very strong interactions between the dimers here. Whereas in the gamma form, it is quite different. Here we have more like different, weaker interaction energies that sort of adds up to more or less the same energy as what we have for the other forms. If that didn't happen, of course, we wouldn't see the gamma form. It wouldn't have been a stable form at all. So what we have done is to collect a large range of diffraction data. We have collected data at many different temperatures, ranging from 10 Kelvin and up to room temperature. Here's a representative look on some of the thermal ellipsoids. We have removed the hydrogens to make it a bit clearer here. The thermal ellipsoids of pyrocinamide in the different forms here at 123 Kelvin and at 90% probability level of these thermal ellipsoids, so that you can easily see what's going on. Now, just from a glance, it's sort of, they look more or less the same, but if we go a little more into to the details, perhaps we can see that the alpha form and the gamma form actually have slightly larger ellipsoids than the beta and the delta form, which could allude to the fact that they are also more stable. They have a higher level of vibrations in the crystals, so perhaps the vibrational entropy of those could be higher, and that could be a determining factor for having a higher stability at higher temperatures. So this analysis is of course very hand-waving, and we would like to do something a little more solid than this. That has been done before. So going all the way back to 1956, we have a very nice paper by Cruikshank, where he derives the entropy of crystalline naphthalene based on doing what is called a TLS analysis, so an analysis, a rigid body analysis of the thermal motion of the anisotropic displacement parameters in his crystal structures of naphthalene. We have done something a little similar in the case of these two compounds, ribitol and xylitol, where we showed that one of the forms actually is stabilized by entropy. And that was also using this TLS approach, whereas Hans-Gert Bürgi and co-workers have been working on a more thorough approach, a very elegant approach, where you use many different temperatures and refine one common model to many different to ADPs from molecular structures at several temperatures. In this case here, for example, for forms of glycine. Yeah, you must follow the reference to know a little more about what's going on here, but combined with also calculations of lattice images, you can actually start to say something about the relative stability of the different polymorphs. Now, I would like to go away from this TLS analysis and move a little more towards something where where I don't have to decide on the vibrations, what vibrations to refine myself. I would like to include all the vibrations in the crystalline state, even the sort of internal vibrations. For that reason, it's nice to be able to calculate the mean square displacements based on theoretical lattice dynamical calculations. And that's exactly what we have done in a number of cases. So we have calculated, and many others have done the same here. You can see a list of references to the right here. You can calculate based on periodic DFT calculations, or even on, you can also use molecular dynamics simulations. You can calculate the thermal ellipsoids, and you can see the difference here between the calculated and experimental ellipsoids coming from neutron diffraction is actually not that large. It's a fairly accurate approach. So with that sort of tool in hand, we can come quite a way. So what is it that we are doing here? We are taking here the dispersion, a plot of the dispersion relations in one compound here in urea in one particular direction of the Bring zone, and we can sort of divide the different lattice or phonons into two regimes. You have the low frequency regimes that actually contributes the largest to the thermal motion, to the not to the thermal motion, but to the anisotropic displacement parameters, and those a little up here, which are the sort of internal modes. I can sort of show it here by starting these small movies here. You can see the high frequencies are the which are up here. The green ones are the sort of internal modes of the molecules, whereas the low frequency modes are related to larger thermal displacements, giving rise to a larger contribution to the atomic displacement parameters that we derive or see from X-ray crystallography. Something is going on there. Okay, so yeah, so here's a plot where I have summed up all these phonon nodes for urea, and you can see that the mean square displacement are fairly small for the heavier atoms here for the internal modes, and they give a fairly large contribution to the hydrogen atoms. And the same if we go down here, we can see for the low frequency modes, the lattice modes of vibration, collective molecular motions. There we have lower frequencies, and therefore we also have higher displacement parameters. So here's the relation between the displacement parameters, the ADPs of one individual atom. It's a summation over all the different normal modes of vibrations weighted by the energy and the frequency of that particular mode. So with that tool in hand, this way of calculating the displacement parameters, we can now combine elastic diffraction or standard X-ray crystallography measurements with these lattice dynamical calculations. So we take some high-resolution X-ray diffraction experiments, we take these lattice dynamical calculations, and we combine them into what I have coined this dynamic quantum crystallography. And from that, we can derive some information about the frequencies of these lattice vibrations, and hopefully we can use that to compute some materials properties and compare, for example, with other types of experiments of that type. So what I just told you was that we could compute the anisotropic displacement parameters by summing up all these lattice dynamical, all these modes of vibrations here throughout the Bring zone. Now, from elastic diffraction measurements, we don't really get information about these phonon dispersions. We only get like a mean. This summation will be kind of a mean value over the whole Bring zone. So to make things a little more easy for us and in agreement with our elastic diffraction experiments, we basically treat each of these phonon modes and the frequency as a mean frequency for each mode. So basically we make things a bit less complicated and use the formula that we have down here, where we basically just sum over each mode one time, and we have the this normal mode eigenvectors that describe the displacement of each atom in this way, that they do not depend on the wave vector, the wavelength basically of the phonon node in the crystal. So what we are going to do is to refine, instead of defining the anisotropic displacement parameters that we normally refine in crystallography, we are going to refine these frequencies of the low frequency lattice vibrations. And we will retain these normal modes that describe the direction and amplitude of the vibration, and only refine on the frequencies which also alters the amplitude of the displacement in different directions. So this is a collaboration with Anna Hoser, and Anna and I have been working for quite a while on this together, and we published back in 2016 and 17 these two papers in ArcticCryst A, where we sort of show how to actually go about doing these refinements, starting from the displacement or from normal mode coordinates and frequencies calculated with the crystal program, but it could be any periodic DFT code. We compute the ADPs, as I have just shown you, and we create input to the ShedX program, and we have used that as a kind of a tool to derive standard crystallographic refinement indicators. And we are then using this we're then changing the frequencies that we originally got from the calculations, from the ab initio calculations, in order to minimize the R factor, so to optimize, so to speak, the structure with respect to the experimental diffraction data. Let's go back to pyrazinamide for a while. Now we have got a detour where we tell about how to treat it. And pyrazinamide, that was where we had these 4 different polymorphs, and we were sort of thinking that perhaps there was a difference in the displacement parameters, and perhaps that would sort of give rise to differences in entropy in the solid state. So on the top row here, you see the experimental ADPs refined with a standard independent atom model, and down here the same ADPs, but this time they have been derived based on this normal mode refinement. And as you can see, there are not that big differences. There are some differences, but okay, it seems reasonable that we have a reasonable model of the anisotropic displacement or the Debye-Waller factors of each of these atoms based on this normal mode refinement. And here we have only, in the normal mode refinement, we have only refined 6 parameters. So instead of all the anisotropic displacement parameters that we normally refine for each individual atom, we only refine 6 frequencies here. So we are using much less parameters and getting almost the same fit, a slightly higher R value than we would get for the independent atom model. With those frequencies in hand, we can derive the vibration to the contribution to the free energy from these normal modes, not only from the modes that we have refined, but also from the remaining modes that are retained from the quantum mechanical calculation. So we have a range of frequencies that we can then use to derive the enthalpy, the vibrational enthalpy, and the vibrational entropy using these equations here. And when we do that, what we end up are these curves here. So for the different polymorphs of pyrazinamide, what we observe here is actually that the free energy is lowered by the entropy more for the gamma form and the alpha form. So the alpha form is the blue curve here, and the gamma form is the green curve. And as we would have expected, we see, or not as we would have expected, but as we have sort of alluded to, we see that these become the most stable ones at low temperature. In agreement with what we had here, the gamma form and the alpha form have the steepest curves here, they get more stable at higher temperatures, and they will eventually overtake and become the more thermodynamically stable forms at higher temperatures. Yes. Okay, now this approach of using these frequencies from this normal mode refinement, we have used that in many other cases, in particular for estimating the heat capacity of different small molecule crystals, using this rather complicated formula down here, but the take-home message is basically up here, that we can actually compare our measure or our derived heat capacities with the heat capacities from calorimetric measurements, and they compare quite well. Actually, Anahosa has performed quite a range of such studies of measurements and comparisons of heat capacities between calorimetric measurements and these normal mode derived or dynamic quantum crystallography derived calorimetric measurements, so to speak, or heat capacities. And here's sort of the summary of that. You can see for many of these small molecules, we actually have quite a good agreement. You can see the calorimetric measurements are the blue open circles here, and if we compare that with the no more model, as we call it, normal mode refinement model, that is the cyan curve here, you can see that that actually fits very well, much better than we actually had hoped for, I think. So we are quite happy with these results. Now, I've promised you that we should jump to something completely different, and therefore I'm going to use a few minutes on jumping to talk about jumping crystals. Jumping crystals is a phenomenon that has been studied for the last decade or so, but actually the phenomenon has been known for a long time. What is a jumping crystal? Well, it's a crystal that performs a solid state to solid state phase transformation at a certain temperature, and along that it makes an abrupt, very abrupt phase change that actually makes the crystals jump. It could also be induced by other things than temperature, for example by light, but in this case here we're looking at L-pyroglutamic acid, and this system actually, as shown here by Wu and company, has some rather abrupt changes in unit cell dimensions as we heat the system somewhat above room temperature here. And there's a certain hysteresis of this phase transformation between these alpha and beta forms, and both of these transformations are related to a jumping phenomenon. How does it look like when these crystals are jumping? I hope I can show you that right here. Okay, it's look a bit strange, but I think if I do it one more time, normally it's better. Yes. So here you can see how the crystal is jumping several centimeters above the heating plate down here. And for some reason, the first time I run this, it looks a bit weird, but I'll do it again. And then you can see it from above here, how the crystal is actually propelling and disappearing as it hits this phase transformation. What is going on here? Well, it's related to a very abrupt change in crystal shape. So there's a very abrupt change in the crystal packing as we go above this phase transformation, and we can compare the two crystal lattices here. Actually, they are not that different. It's very small changes, but they occur very abrupt, and that leads to this very large energy output as we heat the system, and this gives rise to sort of a spring tendency where the crystal is moving. So what have we done with this system? We have tried to measure very accurate diffraction data as good as we could at several temperatures, and this has been performed by Tom Brekes and Anahosa here. Many of these measurements, and what we observe generally is that the measurements at high temperature gives rise to larger thermal ellipsoids. That is not so surprising, of course. When we heat the temperature, the system's temperature, it's gonna have higher thermal displacement parameters. But we were interested in looking at, again, with this normal mode refinements, can we say something about this phase transformation, about the thermodynamics of this phase transformation? And actually, we can, if we only use the DFT calculations, these free energy curves where we sum up all the different contributions to the free energy, they do not cross, so it looks like a monotropic system. But if we use the normal mode refinement approach, then actually we have a crossing of the two free energy curves for these systems at a fairly reasonable temperature, close to what we would expect, or what we observe experimentally as the phase transformation temperature. So that is quite encouraging for the sort of accuracy of our approach here. We have also looked at the same system with the help of Carles Bassins. We have looked at this system using low-frequency Raman spectroscopy. So here we have, again, a waterfall plot of the Raman, low-frequency Raman spectrum going through this phase transformation, both on the heating and the cooling cycles. And what we observe in both cases is a fairly large change in the low-frequency Raman spectrum, again indicating that the lattice dynamics is changing quite a lot between these two crystalline forms. And that, again, we can see also from the theoretical DFT calculations here that the two forms are quite different. I don't know if the agreement with the experiment is perfect, but that's something we are working on at the moment to see if we can make even better calculations. So what's going on in this case? The two forms are quite similar, but we go from the low temperature phase, which is Z prime equals 3 case, so 3 molecules in the asymmetric unit, to the high temperature phase where we only have 1 molecule in the asymmetric unit. And this breaks a certain number of hydrogen bonds. So the hydrogen bonds that are present in the high temperature phase are not all present in the low temperature phase. As you can see over here, the high temperature phase is the red model over here, and it has got these 3 OHN hydrogen bonds, I think, or ONH hydrogen bond it is. Whereas some of those are broken in the low temperature phase. So we were interested in looking at whether we could say something about which normal mode of vibration, which part of the lattice dynamics that is actually involved in the phase transition. Can we see some particular modes that could be kind of the trigger of this phase transformation as we heat the system? There's one particular mode, this mode here, which has got a frequency of about 40 reciprocal centimeters, that actually brings some of these hydrogen bonds in agreement between the two structures. So over here you can see we have, for all the structures here, we have measured the distance of these hydrogen bonds. And you can see for mode number 12 up here, for example, the blue hydrogen bond here becomes much shorter when we actually perform this normal mode vibration. So that could be part of the triggering normal modes that sort of transform one mode into the other. But we haven't found one mode that can explain the entire phase transformation. So it seems that there has to be a combination of these modes in order to bring the low temperature phase to the high temperature phase. Okay, just a few words about the latest sort of developments that we have here. With our normal mode refinement, we have already once looked at how we have studied how we could incorporate aspherical modeling of the electron density into this normal mode refinement. And we used the XD charge density refinement program or multipole approach to look at L-alanine at several temperatures. And what we could see was that once we start using these aspherical models, we can remove, as of course, some of the residual electron density from the bonding region, but we are not fully satisfied, I would say, with the resulting electron density. So there's still some room for improvement, and the latest idea we have is to try to use some other types of aspherical density models and to use it on a larger range of systems to sort of more thoroughly study this phenomenon. And we have had help here from Helena Budkiewicz and Michał Chodkiewicz from the Warsaw group. In order to create a version of this normal mode refinement where we actually go away from using the SHLX program into using something called CalcFCF, which is a small program that Michał has made for us, which based on these form factors that we, for example, can get from the DISCamp server or from different other approaches like the Hirschfeld atom refinement method, which are now all available in the OLEX2 suite of programs. Using those sort of tabulated atomic form factors in a TSC file, we can use Michał's approach or calculated structure factors in our normal mode refinement here. So we can now plug in different types of form factors into our system, and that's something that Helena is looking into at the moment. She has already done it for xylitol and alpha-glycine, and what we can see is that in general we are approaching for the normal mode refinement combined with the TAM model, the transferable atom model here, we are approaching the results where we use the standard anisotropic displacement parameters. So we are getting there, but the densities are still slightly higher. The R factors are still slightly higher. This may be okay because our model is perhaps more physically meaningful than the standard anisotropic displacement parameters that we use. Okay, the last thing I have to say is about the NOMOR server. So if you want to try out some of these ideas, you can go and take a look at the NOMOR server, which is available. It has been set up by Anna Hoser in Warsaw, and it's actually quite easy to use. You need, first of all, to create some calculations. You have to use the Crystal program to create some lattice dynamical ansatz model. And then you have to have, of course, a standard crystallographic model, a SHLX input and HKL file. You have to specify the temperature of the measurements and how many frequencies you want to refine. And then you can actually use that to create these normal mode refinement models. Thank you very much for listening. That was all I had to say. I have a long list of acknowledgements to read up. You can read them yourself. I hope I didn't forget anyone. If I did, I owe you a beer. Thank you very much for listening to everyone.
Thank you. So thank you once again for your excellent lecture. And now we have time for discussion, and we have already plenty of questions. So I will read the question, and then you can answer. Hans Bitbirgi, nice. Anders, have you corrected experiment for first order diffuse scattering? If you did, would the agreement of observed and calc improve or deteriorate?
Yes. Yes and no, or rather no and yes. We have not corrected for first order diffuse scattering. We probably should. I don't have a straightforward procedure to do that. But of course, we have one paper out where we actually calculate the diffuse scattering based on a DFT, ab initio DFT lattice dynamical model. So that could be possible to do, but we haven't done it yet, I would say. But that could be possible. What would happen, you say, if would the OBSCalc improve or deteriorate? Wow, that's a good question. So the the first order diffuse scattering will add intensity basically to the Bragg peaks, and so the thermal motion would look smaller than it does. But how would it? Yeah, then I suppose my guess is that our heat capacities, if that's what you're referring to, they are slightly smaller than the experimental or calorimetric measurements. And so I suppose, in fact, that they would be slightly better, in better agreement if we did this correction. That's my sort of gut feeling, but we haven't tried.
And another question from Hans Bitbergi. Could the delta G curves of polymorphs be made to intersect if you considered anharmonicity?
Yes, that's another thing. Definitely, that would add. That could affect it so that they would cross. We don't have anharmonicity explicitly in the model. Of course, if there is some notions of anharmonicity, they will to some extent be caught up, even if we have harmonic vibrations. They will sort of catch in a way, they will catch part of the anharmonicity in a sort of a quasi anharmonic way. But yeah. So we haven't done that. That is also on the drawing board. There are many things that could be done.
A comment from Jean-Michel Gillet. Beautiful talk, Anders. Thank you for your clarity. And from Jakub Boratyński, thank you. And now we have a question from Maura Maulińska. Thank you for a nice talk. When we are going to be able to tackle ritonavir-like polymorphs?
Yes, okay, so that's a good question. And I think the problem using this normal mode refinement approach will be that the information that we obtain from crystallography, from elastic measurements, is really on the low frequency vibrations. As we go to larger and larger molecules, the amount of internal modes, internal vibrations become larger and larger. And that means that the internal modes become more and more important for the free energy, for the entropy and so on. So we will always need to have to combine with theoretical calculations, and they will be more and more important the larger the molecules. So, but I don't see there's any real reason why we couldn't try out larger molecules. And we have done some, to some extent we have done that, but not the ritonavir-like in size, I would say.
Question from Dashnor Bequiri. Hi Anders, really nice talk. Two questions. Probably a very naive one, but is there a way no more can be used with powder data, or does it only works with Shellick's input? That's the first question.
Yes, I think the idea of using it for powder data is quite good. I like the idea. We have thought about that also. I don't know if there is a way right now to do it, but that would definitely be interesting to try out. I mean, the nice thing about doing it with powder is that we don't have that many parameters to refine. So actually, part of the problem, I suppose, with powder data is that it's really hard to refine all the anisotropic displacement parameters. You simply don't have enough information. But using our approach, we only have a few parameters to refine. So actually, I think it's well suited for looking with powder. We would have to use a different way of calculating the. Now I'm thinking while I'm talking, so I'm not sure that, but I think it shouldn't be that difficult actually. Well, now you're saying it. I think it should be a few weeks of work, then we could make it work for powder data. I shouldn't say that because Anna Hoser will haunt me down for saying that. Anyway.
And the second question, can no more also work with more inorganic crystals like perovskite single crystals?
Yes, I see no reason why it shouldn't do that. I mean, if you can make a lattice dynamical calculation and get the normal modes of vibration, it should work for any system that you would like to try.
A question from Leonardo Correa. Thank you for nice talk. Could ADP be influenced by crystal imperfections in the crystal? If so, this could overestimate thermal displacement influence in ADPs. So how crystal imperfections are taken into account?
Crystal imperfections, and that is a good question. So if we have what I suppose you mean is some sort of disorder, or it could also be substitutional effects. That of course will affect these the measurements and the refinements. And what I didn't show because I couldn't tell you everything, but the gamma form of pyrazinamide is disordered, and there are two very distinct positions of the molecules. They're sort of flipped, and actually the two positions, the atomic positions of the two forms, do not overlap, and that means that we can actually still refine the structure and using this normal mode approach on one of the two phases, which accounts for 80% of the system. So it's dependent on the actual system, I think, and to some extent it will also you may be able to accidentally model some of the disorder as thermal motion, but if what you are after is entropies, you may get a similar effect, right? So you get larger ADPs, which would correspond to having a fairly large entropy, sort of vibrational entropy, or you could model it as disorder, and then it would sort of again add to the entropy. So they are sort of two competing contributions to entropy here, either from disorder or from vibrations, and sometimes they can be hard to distinguish even with this approach, I think.
Carlis Berzins have answered to one of the previous questions regarding inorganic crystals. I can probably answer the second part already. Theoretical calculations for compounds containing inorganic elements can be tricky due to much problematic convergence with DFT calculations. So that would be a technical problem.
Yeah, okay, so that I don't know, having only worked on molecular systems, but again, if we can get a reasonable lattice dynamical model, then we can at least try with inorganics, I think. And there's no problem from the side of normal mode refinements. It may be that the theoretical calculations are not good enough. I don't know.
And comments from Anna Hoser to Hans Birgig regarding second question with delta G curve. They do intersect for pyrazamide. Anders show only vibrational contributions, but in our paper we show that curves do intersect. But we also had the problems with getting accurate lattice energies.
Yeah, that's true. So I didn't show the actual G curves, free energy curves for pyrazinamide, because we have so many versions of those free energy curves, because we cannot decide on the 0K lattice energies. We have many models and they give different answers. So I only showed the vibrational contribution to the free energy.
And another comment by Anna Hoser regarding perovskite. We are trying now with minerals in collaboration with Krzysztof Woźniak and Marcin Stachowicz, and we are getting very nice results for pinoid. So there hopefully soon will be some publication on that.
Yes.
Yeah. Yeah. So we are looking forward to seeing the results. One of the Daniel Kamiński. Did you I know, did you use, or how about using MP2 instead of DFT in your calculations?
Yeah, that sounds like a very hard calculation, very long calculation. I don't know if we are going to try that. I don't. It's not so easy to do with these periodic calculations. I know there is a kind of a plugin to the Crystal program that can do some sort of local MP2. What we have seen until now is that the actual normal mode refinement is not that dependent on which DFT functional we use. So I would guess that we won't win that much with doing MP2, but we could try for a very tiny system like Urea, for example, and see what would happen.
Hans Birgi is writing, so let's wait for his question. So if you say that it's not very much dependent on the type of DFT calculations, can you imagine that you are using very simple approach as a starting point, and then hope for that the refinement will take over?
So even more simple than DFT, you think, like force
Yes.
field or something like this? Yes, that could work out. I haven't. I mean, we need a sort of a setup for doing that, right? I don't know if of any program that can use, let's say, semi-empirical approach or force fields and still produce like a lattice dynamical model. Of course, you could do molecular dynamic simulations. That's also something we are looking into, calculating the ADPs from molecular dynamics. That has been done before, but now comparing it also with a range of methods for DFT in different forms and so on. So we're looking into that a little, but I don't have any nice ready approach to get lattice dynamical model from let's say semi-empirical approach.
And question from Hans Bitbirgi. Have you ever done no more on data of the same compound but collected at different temperatures? And what would be the result?
Yes, we have done that, and we have that for we have done it in different ways. So we have done it for pyrazinamide, and as we heat the system to more room temperature, things doesn't fall out so nicely. It seems like there is a let's say a sweet spot for doing this at liquid nitrogen temperatures, or perhaps up to 200 Kelvin. Then when we go further than that, we start to see perhaps less good data, or perhaps too much anharmonicity to really get good a nice refinement, I would say. It starts to become more problematic. We have also used it in combination where we basically take many temperatures and refine a common model. That have we done in one paper. That can be done, and then you get one model out. But again, without refining a Green-Eisen parameter or anything like anharmonic terms. That has not been done. And Anya is answering, I think, Hans Beers. Yes, so yeah, so of course, Anna Hosa could have given this talk just as well as I could. So it's good that she's now taking revenge and answering questions in the chat, I think.
Yeah. Okay. So Anna Hoser answered D macros we tried once with force field and no more, but is it published?
No,
No,
it's
not
true.
yet.
It's not published. So this is really like, yeah, DMA crystal. This is a rigid body approach to lattice. This is Graham Day's approach for doing lattice dynamical corrections or entropy corrections to his crystal structure prediction code or results. And that we have tried a little. So we have tried it, but for these rigid body derived lattice dynamical models, that we have done, but we have not published it. And I don't think the results were very convincing as far as I recall. Yes.
Okay. So I do not see any more questions. So thank you, Anders, once again for
Thank you so
talk and
much for the
discussion.
invitation, and thank you for the nice questions. That was fun.